Hello, everybody. Welcome back to Grade 11 Physics. Now we're into Unit 5. This is Lesson 1 of Unit 5. We're going to do a quick little review on, some of our uh, electricity stuff. So this unit is all about electricity. We're going to spend a bunch of time looking at circuits. Then we're going to talk about magnetism and how it relates to electricity. And then we're going to see motors as well. So first thing I want to do, though, is go back to Grade 9. Uh, Here we are in Grade 9. Remember we did electricity in Grade 9 science class? So let's think about some of the things that we learned. So what I've given you on our website is what I actually give my grade 9s as their unit test for electricity. So everything on this test, should be what you learned in grade 9. So what I'd like you to do right now is to stop the video and do your best to answer the questions as well as you can. Okay, so take some time here, um, see how much you can recall, and come back when you're finished, and I'll be taking it up slowly. Okay, so right now, stop the video and work on that review. All right, so hopefully you're done that review, and let's go through it now. Okay, so let's see how these questions work. Let's look. So first part was a multiple choice. For number 1, a positively charged object must have. The answer is B, a shortage of electrons. Now you're going to think to yourself, okay, can't C also be correct? Remember, electrons are negative, protons are positive. So if it has a deficiency, a shortage of electrons, that must mean that there's more positives than negatives. And overall, it must be positive. But doesn't it also make sense that there could be more positives than negatives if there's an excess of protons? Why doesn't C the right answer? If you recall, the only thing that can move around in our atoms, remember, when we're talking about electricity, we really are thinking about these from an atomic level, that the electrons and protons in there are what provide the charge. And remember where protons are. Protons are in the nucleus, which means that they're in this tiny little, you can think of it like a grain of sand stuck in the atom, which is like a room. Okay, imagine a room, and there's a tiny little grain of sand in the middle of the room. That's the nucleus. And it's very difficult to manipulate the nucleus. It's this tiny little thing. It's 10 to the negative 15 meters. It's much easier to manipulate the electrons, move them around. That's electricity, is the movement of electrons. So we cannot move protons around. So we cannot have an excess of protons. We can't add protons. Adding protons is nuclear physics. We're changing the nucleus. We can't do that. Okay, if you take carbon, let's say with 6 protons, if you add another proton to that, it becomes nitrogen. We're doing some strange alchemical things when messing around with nuclei. So we can't do that. So the answer is B, shortage of electrons. So remember that. Electrons can move, but cannot move positive charges or protons. Two objects repel one another. What's true about them? They have opposite charge, same charge, one is neutral, or they're made of different materials. Hopefully now you can recall the law of electric charges that says that same charges repel. Opposites attract. How about number B here? A neutral pithball becomes negatively charged. What must the following must have happened? So neutral, remember a pithball, this was this little floating string with a little styrofoam ball on it, or maybe you could use a Cheerio or something like that. For us to make that negatively charged, we had to actually touch it with a negatively charged rod. That negative charge from the rod, those negative charges, those electrons left the rod and went into the pithball and made it negative. Okay? D. Electrostatics is the study of stationary charges. Current electricity is the study of moving charges. Currents move. Stationary, static. 5. Which of the following components is necessary in an electric circuit? Ammeter, that measures current, so no. Television, no. Bulb, no. conductors. There has to be something that allows the electricity to flow, the electrons to flow through a conductor. An ammeter, as I just said, measures current. What is defined as the amount of electrons flowing in the circuit? That is the current again. So for us to, resistance is how much a element of a circuit stops the flow of electricity. Voltage is how much energy per coulomb or per electron, how much kick we're giving each of the elements in the circuit. And current is the amount of stuff that's actually flowing in the circuit. Capacitance, we won't worry about that. That is let's leave that for now. We'll talk about that maybe in grade 12. 8, if the resistance increases and the voltage stays the same according to Ohm's law. Remember, Ohm's law is that voltage, the voltage drop across an element in a circuit, delta V, is equal to the current multiplied by resistance. Delta V equals IR. That's Ohm's law. Okay? If the resistance increases and the voltage stays the same, so if this is constant here, for this mathematical expression to still be correct, the current had to go down. Okay, let's say resistance went from 1 to 2. To keep this as the same, this current value would have to go down. Okay, if I double the resistance, I would have to halve the current to keep the voltage the same. So it decreases. 9. Which type of circuit contains more than one path? More than one path is parallel. Remember, series is one path, parallel is more than one path. Number 10, two light bulbs, A and B, are connected in a series circuit. Switch is closed so that both light up. If bulb B is removed, this is series, so there's one path. If I remove B, then everything goes out. Okay, once you have our circuit, remember your circuit diagrams, something like this, very rough here. This is a series circuit with two light bulbs. If I remove one, then there's no way that the electrons can travel through the circuit. So the answer is D. Quick little matching here for definitions. Power is the amount of energy used in a load, in 1 second by a load. So power is the rate of change. Oh, what happened there? Oh, sorry about that. Something's going weird. Delta E. Oh, it's not going to work. There's a hidden table in there that's making it grumpy. Let's do it up here. So delta E is equal to delta T. It's the power. I'm right on my screen and my head's shaking over there. All right. So the rate of change of energy with respect to time is power. And we did that in Unit 3. So power is the amount of energy used in 1 second by a load. A short circuit is when we have no load. We short past the light bulb, short past the motor, or something like that. That allows the electricity to flow without somewhere for the energy to go. And in that case, the energy has to then go into the conductor or into the battery, and it produces a lot of heat, and they're very dangerous. Okay? Short circuits are dangerous because there's nowhere for the electricity to go. Let's say the battery produces some energy, so then the energy is then released in the light bulb, let's say in a circuit. If I short around the light bulb, if the electricity is able to go past the light bulb without releasing its energy, it has to release the energy somewhere. It releases it in the wires, or releases it in the battery, and we call that a short circuit. The load is defined to be whatever converts the electrical energy into something else. A motor converts electrical energy into mechanical energy. A light bulb converts electrical energy into radiant or light energy. Radiant and thermal energy. Static, we already talked about, not moving charges. Resistance is how much an electrical device stops the flow of electrons. Is my head in the way? No. Okay. How much an electrical device stops the electrons. This is called resistance. Remember, it's measured in something called ohms. Oh, I can't write on this thing. Silly table causing problems. Sorry. So the resistance is how much it stops it. Potential difference is what we call the voltage. It's another name for that. Voltage means how much of a kick I gave the electrons at the battery, how much energy I added to the system, or alternatively, it's how much energy is taken out of the system by a load. Let's say a light bulb is rated for 3.3 volts. So that means that when I put it into a circuit, it takes out 3.3 volts from the circuit. A voltmeter measures voltage. Voltmeter measures voltage. Ammeter measures current. Ohmmeter measures resistance. Quick little Pithball problem. If I have here, this is a positively charged rod. Notice there's a lot more positives than negatives. Here we have if I bring this towards this Pithball, the positive charges are going to attract the negatives, so the negatives will end up on this side. So this side of the Pithball has a negative charge, and this side has a positive charge, which means since this side is also positive, there's an attraction. Okay? Then, when it touches, because they're attracted to this positive, all the negatives transition into the rod, and then once this Pithball has lost all the electrons, lost all its negative charge, it's become positive. I have a positive Pithball, a positive rod, and we have repulsion. Okay, we're treating this rod as like all these electrons basically will just spread out, so it's still a very positive rod. Just since the remember we were using ebonite or acetate. Probably. I'm not sure. I don't recall. I have no idea what you guys did in grade 9. Hopefully this happens. Okay. Sorry. Hopefully you did this or remember doing this. If this one's not too important, just really remember the law of electric charges. Positives, same charges repel, opposite charges attract. That's the big idea of static electricity. Quick circuit diagrams. Draw schematic diagrams to illustrate circuits in series and parallel using a battery, an open switch, and 2 light bulbs. So this is the representation of a battery in a circuit, these lines. Remember that this means that the larger line is positive and the smaller line is negative, which means that the current, we'll talk about that later, positive, negative. Whoa, why'd that move? Some of these don't like me. Plus, it doesn't like, this picture doesn't like me. Oh well, we have it on that one. So series meant one path. So there's only one way that the electrons can travel, which means that the loads here have to be one after another. In parallel, we have multiple paths. So the electrons leave the negative side, they're repelled out of the negative side. They get to this junction here, this dot, and they say, where am I going to go? I can choose to either go to this light bulb or this light bulb. I have a choice here, and it depends on the resistance. The light bulb which has the lower resistance will get more of the electrons, right? Because think about like hallways. If you have 2 different hallways that you can travel through, one is full of kids, one's empty, it's easier to go through the one that has a lower resistance, so more of the electrons will travel through the lower resistance. Okay, but the main idea here is there's a choice, and then once they get back to here, they come the current comes back together, and it goes back to the battery. Okay, so series, multiple paths. Series, single path, parallel, multiple paths. We will discuss this a lot in talking about Kirchhoff's laws. We can actually quantify how many electrons are going to go through each light bulb. Speaking of those, how do we calculate total resistance? Now, once we have let's say in this series circuit here, I have a 4 ohm, 3 ohm, and a 6 ohm resistor. Now, these could be anything. They could be light bulbs, some sort of load that has a resistance measured in these values. Since it's a series circuit, the electricity is going to lose the whole resistance, is just going to be the sum of all of it. So every time we go through another load, we're going to resist it even more, right? So in series, the total resistance is just the sum of my resistances. So I just add them all up, and we end up with 13 ohms as our total resistance. Parallel is a bit more complicated. Because we're going through a bunch of different paths, we're actually reducing the resistance. There's less resistance because there's more places for you to go. Right? Again, using the hallway analogy, or a highway. Let's say this is like a one-lane highway. Right? If you have a whole bunch of cars going on a one-lane highway, they're limited by the one lane. But now I'm going to expand it into a 3-lane highway. I can get a lot more cars, a lot more current through the highway. Right? Every time I add another path, I'm going to actually reduce the resistance. Mathematically, we can use this expression here. 1 over RT is it's like an inverse. 1 over R1 plus 1 over R2 plus 1 over R3. We'll derive this in lesson 3. Okay, we'll derive where this equation comes from. Let's just use it for now. It's at the bottom. If you scroll all the way to the bottom of our test, the equations are all here. However, we're going to actually derive it. Let's just not worry about it for now. So let's plug in the numbers. 1 over 6 plus 1 over 3 plus 1 over 2. To add these, we have to get a lowest common denominator, in this case 12. We end up with 1 over R is 12 over 12 ohms. So then to get the resistance, our total, we have to flip both of these. Right? Since this is 1 over R, to get RT by itself, we just flip it. And then we flip it and we end up with 1 ohm. So notice 632 ohms in parallel actually has a much lower resistance of only 1 ohm. Okay. Light bulb uses 120 volts and 3 amps. Calculate the resistance. So again, we're going to use Ohm's law here. V equals IR. Solving for R, we're going to divide both sides by I. And then replacing V with 120, I with 3 amps. We end up with 120 divided by 3, which is 40 ohms. What is the current through a 12-watt bulb and attached to a 10-watt bulb attached to a 12-volt battery? Power is voltage times current. Okay, this makes sense because the voltage is how much. You can think of voltage is the energy per charge. I'm going to use Q as charge, and then the current is the charge per time. Okay, that's what current is defined as, how much charge is traveling through our circuit in a certain time. So if I multiply V times I, I'm going to get E over Q multiplied by Q over delta T. Q's will cancel, and I end up with the energy, the rate of change of energy with time, which is the same as power. So P equals VI. We're looking for the current though, so we're going to have to rearrange this, get I by itself, divide both sides by V. So it's going to end up with 10 divided by 12, so we end up with 0.83 amps, going to 2 significant digits, assuming that this 0 is significant. Assume that this has 2 significant digits. Let's see, number 4. A USB charger outputs 1.2 amps, the current of 5 volts. What's the power? Much simpler this time. We don't have to rearrange. Again, P equals VI, plugging it in. I really should have rounded this to just 5 because 1 significant digit on the 5 volts. Okay. A 100-watt light bulb is used for 8 hours a day. Determine how much it costs in 1 year if 1 kilowatt hour costs 8 cents. So since we know that power is energy divided by time, energy is going to be power times time, right? Multiplying both sides by delta T. So that's going to be 100 watts multiplied by the time in seconds though, right? Remember a watt is a joule per second. A joule per second. So we have to multiply by the time measured in seconds. So we need 8 hours. Oh, I didn't finish this. So this is in 1 day. It's going to cost 64 cents. So it asks though for the yearly cost. So we're going to have to multiply this by 365 to get a final answer, which will be 0.064 times 365. So it's $23.23. Okay, Apologies, I didn't finish that. Okay. All right. So, correct your answers. Hopefully that helps. And we can move on from there. Okay, and then we can get to new stuff now. All right. So, thanks for hanging out with me and going through all these solutions. All right. Take care.